I'm going to do this presentation in English this time. So the presentation is about token probabilities to mitigate large language model overconfidence in answering medical questions. It's basically a quantitative study to assess the difference between the reported token probabilities in chat by the model compared to the actual token probabilities accessed via the API. It's done by researchers, mostly doctors in Lille in a university hospital in France. I've added the link if you want to check it. So let's go over the overview. So what is the problem with using medical LLMs? They validate that what researchers found was that token probabilities significantly outperform self-reported confidence in predicting LLM response accuracy on medical questions. They tested 9 LLMs across 12,000 medical licensing exam questions across 5 countries and languages. The key results that were found were that the self-reported confidence was between the range of 0.5 to zero point 0.7, while the actual token probability was found to be between 0.7 to 0.87. All models showed overconfidence. That is, they were overconfident on even in the wrong answers. What was the practical impact? When we use token probabilities as a method of assessing whether the answers were correct or not, the false positive rate was reduced from 91% to 37%. That is more than, I believe, 300% increase in performance. The the most well-performing model was GPT-4o with 98% accuracy on high confidence answer. To give you a better overview of what I'm actually talking about, I've also created a very small comic. We'll come to that later. So what was the reason for doing the study? The previous works and motivations were as follows. LLMs have started to achieve passing grades on medical board exams, namely USMLE, Taiwan's medical exam, China's medical exam, even the French medical exam, which in turn builds trust for chemical deployment. However, chatbots systemically express high confidence regardless of actual correctness, which is simply not tolerable in the medical field. You need the answers to be 100% accurate and 100% correct. Prior work, Krishna et al.'s GPT-related confidence, 8 out of 10, was even when wrong, GPT reported 100% accuracy, even when it was wrong, and 77% in the case of GPT-4. Token probabilities represent the model's internal mathematic certainty, which is completely separate from what it actually says in the chat. In order to better understand what I'm talking about, I've created a small comic which you can look at. So basically, it's this: a doctor uses a medical LLM and gives the diagnosis of cancer to the patient. But the patient is skeptical about the diagnosis because he says that the only symptoms that I have seem to point to just a simple cold. When the doctor actually checks the internal probabilities, it's found that the patient was correct, and the internal probabilities pointed to cold, not cancer, which is very harmful for the patient, doctor, and everybody involved. So what's the big question? The big question is, can token probabilities provide a more reliable measure of LLM uncertainty than self-reported confidence? To answer this, the researchers has had an experimental setup in which they had three commercial models and 6 open source models, namely GPT and Llama 5 Gemma. Why were these chosen? Because these were the models with API access to log probabilities. What kind of medical benchmark was used? 12,619 questions from US, China, Taiwan, France, and India. Medical licensing exams were used for a benchmark. So what did it demonstrate? It demonstrated token probability superiority. That is mainly AU ROC improvement from 0.51 to 0.7. X was expressed in chat as I iterated earlier, while the real token probabilities were found to be between 0.7 and 0.87 across all models with p-values less than 0.001. And the practical recommendations for token probabilities are easily accessible alternative for detecting inner doubts of LLMs in high stakes settings. Preliminaries. So what is actually the problem setup? The models were given a task of multiple choice medical Q&A question with a single answer. The inputs were question, answer options, and language instruction. The output was selected answer letter with confidence rating. The prompt was as follows, which this is taken directly from the paper. Select the letter corresponding to the correct answer. In addition, please rate your confidence in your answer from 0, not confident, to 100, absolutely confident. Your output must follow this template with no additional comment. The correct answer is letter, my confidence level is number. Two confidence measures. Express confidence, self-reported in model output. My confidence, that is, my confidence is 95%. And token probability, internal probability assigned to answer token, A, B, C, D, E. P, and the evaluation metrics were, there were three evaluation metrics which are used: AUROC, adaptive calibration error, and Breer score. So why did we choose these nine models? As stated earlier, these were at the time of the study, these were the SOTA models, state-of-the-art models, with log probability. That was the reason why Gemini and Claude were excluded from these studies, because at the time of the studies, these models did not provide internal probability calculation via their API. Most of the models range have a range. The model parameters have a range of 8 billion to 70, with the smallest being Llama 3.1 at 8 billion, and the largest is namely GPT-4o, but its small parameters are not public information. So, in the database and experimental setup, around 2,500 questions each were used from medical tests of each country. However, the point to note here is that the passing grade in each of these medical exams for humans is like, for example, your doctor who you might go for everyday ailments is 60%. That is, if you score more than 60%, congratulations, you can practice medicine in that country. The lowest score being 50% and the highest being 60. What was found for so how did these LLMs perform in on these medical exams, you might ask? It's GPT-4 came at highest with 89% performance, and 7 out of 9 models passed these medical tests. The only two models which did not pass were, of course, the open source open weight models, that is Gemma 2 and Phi 3 Mini. But even these models barely missed the mark at 59% when the passing grade was 60%. So what does this mean? So that the model scored 89% on the test, well above the passing grade. Does this mean that we do no longer need human doctors? Does that mean that human doctors are not incapable enough? No, that is simply not the case. Why is that? Because of the overconfidence problems. All models express extremely high confidence regardless of correctness. That is, even when they were wrong in their diagnosis, they might have expressed that, oh, I have high confidence in this answer and this answer is correct. Confidence expressed in round numbers for mimicking human patterns. For example, if I ask you what percentage of this presentation have you understood up until now, most of the humans in this attending this meeting might express their percentage of understanding in round numbers, 70%, 60%, 65%. But that is not really the case. If you actually test them on their understanding, the answers which might come out won't be round numbers. It could be 63%, 74.5%, and as such. Similarly, models mimic this human behavior. Models express greater than 80% confidence even when being completely wrong. GPT 3.5 expressed 100% confidence even on incorrect answers. While GPT 4, the best performing model among the lot, had 77% of wrong answers with high confidence. So token probability versus expressed confidence. Token probability consistently. So how can we tackle this problem? Of course, we'll use token probability. Token probability consistently outperformed express confidence. That is, all p-values being less than 0.001. Improvement. The model's performance being went from being barely better than random, taking randomly choosing a diagnosis, to being genuinely useful prediction. The moment that we started using internal token predictions. Uh, the practical impact, false positive, reduction in false positive rates. How often do how high confidence answers turn out wrong? Using token probability dramatically reduces false positives. Cheaply 3.5, as stated earlier as well, went from 91% false positives to 37%. That is very near to the human real life human rates when uh, when when referring to false positive diagnosis rates. There were multiple graphs in the paper. However, I've only attached GPD4 for your reference, which is because it's the best performing model and it's the most easiest one to understand. Calibration analysis. Are models well calibrated? All models showed, you might ask, were the models fine-tuned or were they calibrated at all? The answer is no. The models were used in the vanilla state. And in this vanilla state, they showed tendency towards overconfidence. Of course, smaller models with fewer parameters exhibited worse calibration. ACE was greater than 40%, for example, for 5-3 many. However, we must note that 5-3 many actually failed the test and scored 59%, 56.5%. So it was actually the lowest performing model among all 9. Token probably improved Brier scores across all models with p-value becoming less than 0.05. That is a significant boost from the previous of p-value being less than 0.001, namely more than 100 times. Pattern, the pattern is of course very obvious that high performing models had better calibration for both metrics. Result sensitive analysis. Uh, Multilingual data sets are results robust across conditions. That yes, what we found was that the results were consistent across regardless of language. That is English, Chinese, and French. Exception, smaller models showed lower performance on mainland China data set. But this is simply because these models, smaller models, do not have access to large swaths of data set, unlike large models, which are made by labs with significant better funding and access to better data sets. Prompting strategies, the vanilla expert few shot confidence scaling show that few shots slightly improve the performance of GB 3.5 and Llama 3.18 billion. AUC increased from 0.03 to 0.04. Knowledge type, no difference was found between step 1 basics and steps 2 or 3, that is namely clinical. Alternative metrics which could be considered would be Shannon entropy and perplexity. However, these were not used in the study this time. So why does this happen? The model has this accurate internal sensitivity, it just doesn't share it. That is, and when a normal general user uses the model, all they have in their frame of mind or reference is a ChatGPT web interface. They don't even know about the existence of internal token probabilities or anything such a metric exists as such. And another problem for these LLM models is that they're trained on data generated by humans. And humans have this problem of expressing confidence in large round numbers. And these LLMs mimic these patterns as well, similar to humans. They express their confidence when asked in chat in large round numbers. They avoid explicit uncertainty and have exaggerated expressions, absolutely certain, being the most common one to detect LLM generated text. Key insights, self-reported confidence is another form of generation, not introspection. The model plays a character mimicking confident human, even though it is not a confident human, it is just simply mimicking a confident human, which is completely different from its internal state. So what were the limitations of this study, namely being that the single choice questions were only asked in this test, which is not the scenario in real life. Findings may not apply to free text responses spanning multiple tokens. Methods of aggregating token probabilities is still under development. Secondly, limited prompt engineering was done. Deliberately, we used a very simple prompt with default configuration to mimic real world usage, and other techniques which could have potentially impacted the outcome or even improve the outcome were not used, just to simply mimic the real world scenario in which you go to your doctor and just tell them your symptoms without having any explicit medical knowledge yourself. there are models which do not really give access to the internal token probabilities, namely Claude and Gemini, could have probably performed better in these tests. However, we could not assess it because of inaccessibility to the internal token probabilities. Reasoning models O1, etc., involve multi-step decisions. However, these were not used again to keep the complexity of the project to minimum. To reduce the complexity of the project. Practical implementation, we need an interface designed for communicating uncertainty to clinicians who do not have a background in AI and might not understand what internal token probabilities actually mean. Integration into clinical workflows obviously remains unexplored for now. So, to summarize, LLMs perform well on medical exams, 56.5% to 89%, but systematically overstate confidence. Self-reported confidence is nearly useful for predicting accuracy. AURC was found to be, as I reported earlier as well, be zero point 0.5, between 0.5 to 0.7. Token probabilities significantly outperform expressed confidence, with AURC starting from zero point 0.7 and ending at 0.87. And token probabilities are already via API. We don't need any special techniques to calculate it. But however, this is only true for commercial models or models hosted on any API service. If you plan to use your own service, such as an own open model locally on Llama CPP or VLLM, you might need an explicit another setup to actually calculate these token probabilities, further leading strain on the limited computing resources. Recommendation of this study was to use token probability thresholds to flag responses, which in turn could be forwarded for expert review. My personal take is that this connects to the broader questions about LLM self-awareness. Models have useful internal signals but don't surface them naturally. Interface problem. Not it. I believe it's an interface problem. It's not a model problem. We need to redesign how we present AI to general users. Thank you. はい、以上です。
Hi. Thank you for the presentation. And anyone has a question or comment for this presentation?
はい。じゃあ、ちょっと質問いいですか？
はい。
今回の論文は、医療の LLM について、ロジットを使って性能向上したって話だったと思うんですけど、実
はい。
際LLM の研究の中でも、ロジットレベルのコンフィデンスがまだ全然完璧ではないっていう研究いっぱい出てると思ってて、で、今回の、検証の中でも、多分ロジットが高いから選んだけど、結局間違ってたみたいなところは結構あったのかなと思うんですけど、そこについての分析みたいなのってあったりしたんですかね。もしあったら知りたいなと思って質問しました。
はい、そこで、ロジットに関してですね、ロジットが基本的にどうやってアクセスしたのが、基本的にこ
うん
の論文のメインになります。で、二つのやり方ですね。一つ目が、チャット
うん
で自分のロジットを教えてください。で、そこで教えたロジットが実際のロジットとだいぶ外れてる。実際に
うんうん
API を使ってロジットをアクセスしてみたら、だいぶ外れてる
うんうん
ってことがあったっていうことで。そのた
あ
め、
ーうん
新しく、今までベンチマークとかもいろんな LLM でベンチマークやってるじゃないですか、MMLU とか。そ
はい
こで普通にプロンプトを与えて、回答をそのまま評価するじゃないですか、今もベンチマークで。で、新しく
はい
ベンチマークとして、これがロジットを使ってした方がいいんじゃないかなとも
うんうんうん
思いました。そのために、なんか医療論文を発表するより、ロジットが新しくベンチマーク技になることじゃないかなと思ってます。
あーじゃあ、セルフコンフィデンスで自分でロジット出力させるより、ちゃんと内部のやつ取った方が、それは性能が上がったよっていうのはあるけど、そもそも内部の計算のない段階でロジットが正当とずれてるやつは、えっと、今回の論文の範囲だとちょっと回収しきれないっていう理解ですかね。
はい。そう
あ、
です。
はい。なるほど。ありがとうございます。
他はどうでしょうか。実感も来てるんで、発表としては分かりやすくてよかったと思うんですけど、多分この論文自体は多分ジャーナルですよね。確か。
はい。
そうですよね。だから、さっきの大阪さんの質問にもちょっと関係するんですけど、割と手法としての新しさみたいのは、そんなないんじゃないかと思ってて、バーバライズするのと、ロジットで比較するみたいなのも、比較的よくある話なので、なんていうか、まあ、ちゃんとやった研究だっていう感じの位置づけなのかなと思って聞いてはいましたし、まあ、一次参照情報としては、面白いというか、ちゃんと実験した結果っていう感じの位置づけかなと思いますというのが、このコメントで、その上で、まあ、大阪さんが言ったように、その後の手法としての議論はもっといっぱいあるんで、なんかそこら辺は深掘った方がいいかなと思いましたっていうのと、これ、ちなみに、バーバライゾっていうか、何でしたっけ？どう書いてましたっけ？自分で説明させるやつは、これロジットをそのまま出させてるってことでいいんですよね。
そうですね。チャット上で自分のラジットいくらですか教えてくださいと、API を使って実際のロジットを調べてみたと、ずれてる差があるってこと。
うん。あ、わかりました。で、そこももっといろいろ方法あるので、実際には、なんか、最も基本的な2つの方法っていう感じだと思いますで、例えば、だから外部のベリファイア使うとか、その思考過程出させて、思考過程が正しいか見るとか、そういうの含めて、結構いろいろやられてると思うんで、その辺は調べてもらった方がいいかなと思います。
わかりました。
はい。じゃあ、特に他に質問なければ、一旦ここまでしようかと思います。はい。